All right, we're going to be looking at labeling this reaction coordinate diagram. And if you remember back when we talked about thermodynamics, we had seen a diagram similar to this, except it only had this potential energy of reactants and potential energy of products. So this whole center section here was not there. So again, we looked at this before. We were looking at the overall energy change or enthalpy change of reactants versus products in the course of a reaction. And we were looking at the amount of energy the reactants had versus the amount of energy the products had. We didn't see this big hump in the middle. So what this is showing us well, we call it a reaction coordinate. It's showing us the potential energy changes over the course of the reaction. So notice as we move from left to right, that's time progressing or the reaction progressing. This is the reaction that we are looking at. So A and B are the reactants, C and D are the products. And so we look at our first question. It says the above reaction, is it endothermic or exothermic? So again, endothermic means the reaction absorbs energy in order to make the products. So that means that the products end up having a higher stored enthalpy than the reactants do. If it's exothermic, that means the reaction releases energy and energy is produced as a product. So aside from seeing the reaction equation written down here where we see energy written as a product, we also notice that here's our initial reactant energy, here's our final product energy, and so we looked at the difference between the two, and the reactants start out at higher energy and the products end up at lower energy. So that means that overall the stored energy is decreased, and that would be exothermic then. So you should indicate that on your worksheet for number 1. What letter represents the potential energy of the reactants? So again, here's my reactants, A and B, and so the total amount of energy the reactants have would be indicated by B. So for number 2, that's B. Number 3, what letter represents the potential energy of the products? Well, again, here's the products, C and D, so the arrow labeled F would be giving us the amount of energy for the products. What letter represents the heat of reaction, or delta H? So that is remember, it's always going to be enthalpy of products minus enthalpy of reactants. So the difference between F and B, and so notice the difference between F and B is going to be actually D here. So notice that this is marked from where my product energy is up to where my reactant energy is. So this would of course be a negative value, but D would be the numerical value for the delta H. Number 5, what letter represents the activation energy of the forward reaction? Okay, so activation energy, we saw that mentioned in the video we watched the other day on reaction rates. Activation energy is the amount of energy that's needed to be input to get the reaction going. The thing with activation energy is you can always find it by looking at the top of this hump in the reaction coordinate diagram. However, we have to know where to measure activation energy from. So we know that our reactants start out at some amount of energy, and so the amount of energy that is input above where we're starting, that's the activation energy. So what I mean by that is to measure activation energy, it's going to be, well, here's my reactant starting energy. I'm just going to draw the line out so I can see it in relation to the hump, and then up to the top of the peak, that's going to be, so this amount of the red arrow that I drew. So notice that that is actually what this arrow A is indicating. So it was drawn from the reactant energy up to the top of the peak. That's going to be the activation energy. So you're not just labeling the activation energy just, the total amount of energy here, right? It's not C, it's A. So it's the distance or the amount of energy from where we started with reactants. The reactants have some potential energy, and that's up to the top of the peak. And so this would be letter A for number 5. So you also notice it says something about the forward reaction. So that's reading the equation left to right like we're used to, reactants forming products. We are going to talk about reverse reactions in upcoming days, and we'll also have a question about that later on in this worksheet. So again, forward just means reading left to right. Okay, so moving on to number 6, what letter represents the potential energy of the activated complex? So the activated complex is, in the process of this reaction, the stuff that appears like the intermediate, might not necessarily be compounds, might be just in that transitioning between breaking bonds and forming bonds, the stuff that exists when we get to this peak energy. And so then the activated complex is the the transition state kind of between the reactants and the products. And so the potential energy of the activated complex, well, that's what C is actually representing. So that's that stuff that's been created, and by adding the activation energy, the amount of energy needed to get up to the top of this peak from where we started, well, the total energy of that stuff, that is what letter C is representing. But again, normally we won't be labeling the potential energy of the activated complex. We're just going to be labeling the activation energy. But for number 6, that would be C. Number 7, if a catalyst were added, what letters would change? So again, a catalyst works to speed a reaction by lowering activation energy. So what's actually going to be different is the height of the curve. So notice, actually, let me do this in a different color. Let me erase all the ink on the slide and do this. Well, now it doesn't need to be a different color, I guess. So what a catalyst does is it's going to keep us at, my reactant energy doesn't change, but the height of this peak will change. Depending on the catalyst, how much that goes up or down, that's going to vary. But sorry, how much it goes down will vary. But my energy, my beginning energy, I can't seem to draw a straight line, but my beginning energy and ending energy, that stays the same. So that's important to note. This is exactly the same amount of energy as what we started with, but the height of this peak decreases. And so it's the activation energy arrow that's going to change, because that's what our question actually asked us about. So for catalyst, we are lowering the height of the hump, we're lowering the amount of activation energy, and that would be letter A that we lowered the value of. For number 8, is the reverse reaction endothermic or exothermic? So the reverse reaction is the reverse of whatever the forward is. So my forward reaction, we read left to right. My reverse reaction, we read right to left. And so if I were to start with C and D and form A and B, well, the reverse reaction, notice I'd be going from lower energy to higher energy, so that would be endothermic. So the reverse reaction is always the opposite of the forward reaction. So if we said the forward reaction was exothermic, then certainly it makes sense the reverse would be endothermic. And lastly, what letter represents the activation energy of the reverse reaction? Well, again, activation energy is always measured from your starting point. So in the reverse reaction, my starting energy would be for the products, right, which are actually acting as the reactants in the reverse reaction, up to the top of the hump, so that hasn't changed. So this difference in energy between the product energy and the top of the peak, that is the activation energy of the reverse reaction. So that would actually be letter D. I'm not really going to be having you label that in the future, but we just should recognize when we start to talk about these reversible processes that if I want the activation energy for the reverse reaction, you're going to do the same thing that we talked about for the forward, except our starting amounts would be these things written on the right side of the reaction. Okay, so let's move on to the next page here, the back of your worksheet, B1, and we're comparing the graphs here. So this is showing the distribution. It says fraction of collisions on the y-axis, says energy in kilojoules on the x-axis, and then we've got this reaction coordinate diagram, just like we just saw on the front page for figure 2. So number 1 says compare the frequency of collisions at point A, B, and C. So notice, just looking at the height of the curve at these different points. So here's point A, here's point B, here's point C. Notice that the highest value is at point B, right? So what that means is that at this amount of energy that B aligns with, so it's, I don't know, kind of around 25 kilojoules. I can't seem to draw a straight line. That's the majority of collisions are happening with that amount of energy. That's what that means. For A and C, we have roughly, if you look at where the curve is for both these points, we have roughly about the same amount of collisions for A and C. Okay, so circle 1. So there are fewer or more collisions with energies greater than 50 kilojoules. So here's 50 kilojoules. So if we look at what this curve is showing us, what that means is there are, well, let's see here. So higher than 50, notice there's a smaller area of the curve that's at greater than 50 kilojoules, and there's a larger amount of the curve at less than 50 kilojoules. So we would say that there are fewer collisions with energies greater than 50 kilojoules, because the majority of them are less than. So you're circling fewer than for the first point in number 1. At this temperature T1, so notice this graph is for a specific temperature, T1, there are no gentle collisions, and that means a collision less than 15. Well, notice that here's A, and that's actually at 15 kilojoules, and so there are collisions at less than, so see how there's some of the curve is to the left of 15 or less than 15 kilojoules. So that certainly is false, because there are some gentle collisions. So again, we're talking about the energy of particles at a given temperature. Remember we said that the average kinetic energy is the same at a given temperature, but there's a distribution of energies with which the particles are traveling. So we still do have some at lower energy, and that's what that question is asking us. So second thing there is false. The third point under number 1, at this temperature T1 there are no energetic collisions greater than 70 kilojoules. Well, here's 70, and notice there are a few things. We're looking at where the curve is. It's not at 0 yet. It's getting lower, but it's definitely not at 0 yet. And so we would say that that is false, because there are energetic collisions with energy greater than 70 kilojoules. So both of those true and false statements are false. And the collision energy of most collisions, well, let's look at the highest peak here. And so the majority, we already mentioned this before when we were looking at B, majority of the collisions are happening at about 25 kilojoules. So you would fill that in the blank on number 1, the collision energy of most collisions. So this is where the peak is the highest. That is 25 kilojoules. Okay, so for number 2, in order for a reaction to occur, molecules must have sufficient energy. This is called activation energy. And so when we look at the graph on the right here, we just talked about how to find activation energy. So we're going to label the activation energy on this graph on the right here. So again, we go from the, not the bottom of the graph, but from where my reactants are starting. So the reactants start out at 10 kilojoules. And again, I'm just going to draw my line over just so I can see it. Notice the top of this peak is at 50 kilojoules. So it's supposed to be a straight line, the energy input from where my reactants start up to the top of the peak. Well, that's a difference of 50 minus 10, so that's 40 kilojoules. So that would be my activation energy, is 40 kilojoules. And so that's what you're writing in for number 2. Label the activation energy from question 2 on figure 1 by drawing a vertical line. Okay, so we said 40 kilojoules, and so let's put on a different color here. 40 kilojoules, it's right here. So that's at C, point C actually. It's supposed to be a straight line. Okay, so there's my activation energy labeled on figure 1. So that's what 3 asked me to do in red there. Shade in the area under the curve on figure 1 representing the fraction of collisions that have enough energy. So any particles that collide with 40 kilojoules or more have enough energy to react, right? They have the minimum activation energy required. So anything above 40, so any of these particles, so I'm going to, why don't we try the highlight feature here? So any of these particles above 40 kilojoules of energy when they collide, so anything I'm highlighting in yellow here, those have enough energy in order to react. So for D, do all the molecules at T1 in figure 1 have enough energy to react? Well, no, not all of them. So that's why we're going to have some collisions that are not effective. They don't have enough energy when they collide, anything with less than 40 kilojoules. And that's a big area here, not highlighted, but we do have some that will react, which we highlighted in yellow. So for for number 5, no, not all molecules have enough energy. Number 6, on figure 1, sketch a possible frequency distribution for molecules at a higher temperature. So remember that higher temperatures, we are going to have an increase in average kinetic energy, and so that means we're going to have an increase in speed, particle speed, and so we're going to have an increase in the collision energy. So this is not something you would know off the top of your head, but the way these distributions look, we know that the energies of collisions are going to be shifted to the right. Our graph is actually going to get flattened out a little bit as well, and that's just a statistical feature that, again, I don't expect you to know. But again, we'll notice that the peak has been shifted to the right. So that's the most important thing when you're drawing your peak on, is that the energies are shifted to the right, because we know at higher temperatures, particles will collide with more energy. And so after we drew this, it says compare T2 and T1. Are there more or fewer molecules with energy to cause reaction? So again, our guiding line is at 40 kilojoules. So any particles with more than 40 kilojoules of energy are going to be able to react. And so notice my area under the blue curve is actually increased in size. And so we're going to have more particles with sufficient energy to collide. And then for number 7, true or false, increasing temperature reduces the activation energy needed for the reaction to occur. Well, notice I didn't change this 40 kilojoules. This information over on the graph on the right, that hasn't changed. The initial amount of energy for the reactants didn't change. The top of this peak, the energy for the activated complex, that didn't change. So the difference between the two, which is the activation energy, that has not changed. So in answering the question, has my activation energy changed as a result of temperature increasing? No, it has not. It's still 40, as I labeled on the graph originally. So 7 is false. And so you're going to write the conclusion yourself, and this is what we'll go over in class. Increasing temperature increases reaction rates because, and so you need to think about that, write it down, and then we can talk about that in class.